what we mean by a control system. Then from that it proceeded. That is, what are the control system inputs? The control system input is basically the stimulus that is applied to a control system from an external source, obviously, to produce a specific response from the control system. That is the desired response that will drive the desired controlled variable to the desired level. Okay. Then what is the control system output? In response to this control system input or the stimulus, the actual response that you obtain from a control system. Right? And we have clearly defined upon two types of control systems: open loop control system and closed loop control system. In open loop control system, the performance or the operation is independent of the output because there is no arrangement of measuring the output and feeding it back to the control system. Whereas in a closed loop control system, the control action is dependent on the output. Since we have a provision for measuring the output and comparing with the set point and then determining the required action. Okay. So this is the basic difference between open loop and closed loop control system. And the information that we have at our disposal is output information. It's called the feedback information. So this gives you an idea about the present condition of the process variable or the controlled variable that you want to control. So the controlled variable is that process variable which is maintained at a specified value or within a specified range. Correspondingly, what is a manipulated variable? A manipulated variable is that process variable that is acted on by the control system to maintain a controlled variable at the specific value or within the specific range. You can say the controlled variable is the result of the variation in the manipulated variable that is being decided by the control system based on the feedback signal available with reference to the set point. So these are the some aspects that we discussed in the last class. So without dealing with some other terms, let us put up an example. Right? If you can remember, bolo, yes, PDF টা হ্যাঁ প্রসেস কন্ট্রোল পিডিএফ এর নামটা আচ্ছা বেসিক বলো
স্যার পিডিএফ এর নামটা কি
ওকে 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 আচ্ছা ওটা হচ্ছে আমার ওকে ওকে ওটা কিছু না ওটা আমি জানি না আমার মানে আমার অ্যাডোবে কোনো একটা বাগ আছে ঠিক আছে জাস্ট বিকজ অফ দ্যাট বাগ ওটা দেখায় আমায় there is some problem with your country তো there is something terribly wrong with this country isn't there এটা যে কোনো পিডিএফ খুললেই আমার এই প্রো ভার্সনটা এটা অ্যাকচুয়ালি একটু তোমার পাইরেটেড ঠিক আছে ওটা আমি যাকে যাকে দিয়েছি যারা যারা ইউজ করছে এই ভার্সনটা সবাই আমাকে কমপ্লেনটা করেছে লাস্ট এই এক্সটেনশনটা কেন আসে আমি জানি না এটা ম্যাডাম ভেবো না যে কোনো আমি কিছু করেছি no, it is satirical, but I have nothing to do with that. I have tried everything, but I couldn't manage যে কি করা যায় ওটা. So I think, yeah, তোমার point out করলে ঠিকই. From a neutral perspective, it may seem that I am anti-nationalist or something like that. Nothing like that. It is some bug in the PDF. Okay, so I am not being able to update that. Sure, if you have noticed that, I think now it's time I should move on and put some other version. Since it is see Adobe Acrobat Pro extended, so it required some crack, and I think in that crack that bug was there. So don't judge anything. So this is a basic control loop that we discussed in the last class. This is your reference point, set point, which is being compared with the feedback signal, and feedback signal is obtained from the controlled variable output by the feedback elements that constitute sensors, transducers, and signal conditioning elements. Now, this reference signal, when compared to this feedback signal, will generate the actuating signal or error signal, which will be fed to the control elements and the control system part, where it will be controller. This controller will determine, based on this difference, what control action need to be taken, and that will be translated in terms of this manipulated variable, which will cause some parameter to change in the plant itself. Okay, and this entire process will be subjected to disturbances. Since we normally see in process control, this reference input is more or less constant. So all other activities will take place subject to a disturbance that tends to change the state of the control variable, right? Under the disturbances, we have a variation in control variable and we need to take corrective action. Okay, so let us move on and see an example. I think as long as I'm not giving an example, this block diagrams will not speak anything. Right? I'll just check intermediately whether new participants have come or not. Yes, as getting an indication here. So if we take an example now, let's see. So the example that I'll be dealing with is the temperature control of lubricating oil. You all know that lubricating oil is normally used in positions or in locations where there is some mechanical parts involved with motion, relative motion. And lubricating oils are normally used to reduce the frictional component in that motion. So what it does, it not only reduces the frictional component, it also takes up some heat. That means even if you can avoid that friction between two moving solid portions, you cannot completely eliminate the viscous friction that will be present due to the presence of this lubricating oil. So as a consequence, the lubricating oil will be getting heated up, and this temperature of this lubricating oil cannot be allowed to increase beyond a certain level, because these lubricating oils perform their job at a particular temperature range, so that their lubrication property is appropriate or adequate for a particular operation. If the temperature of the oil becomes too hot, then the lubrication property may get deteriorated, and therefore the purpose will not be served. So we have to maintain a system where we can maintain the temperature of the lube oil to a particular level or within a range of acceptable value. Now, what is the arrangement that you normally follow? See, this is your lubricating oil cooler. In this chamber, there is basically tubular motion through which the lubricating oil flows. Pardon me for my drawing. This is basically a chamber through which it's flowing, and this is enclosed by this chamber. Okay, this is given here, and through this chamber, water flows. It comes through here and goes out like this. And oil never leaves this what is a tubular path. So oil flows within this tubular path, and cooling water normally flows to this chamber, entire chamber, taking the heat away from the oil. And at the output, we'll get the cold oil. Now, to maintain a temperature control system, what you need at the output is a temperature transmitter, which will sense the temperature and transmit that signal to a temperature controller, which will measure this transmitted value and compare it with a set point. There's a range of value or a particular set value at which you want to maintain the hot oil or the lubrication oil too. So depending upon this, whether this temperature is greater than the set point or less than set point, this temperature control valve will be opened or closed. What does this valve do? Opening this valve will cause more water to flow through the tank, and closing the valve will cause the flow rate to get reduced. So depending upon whether if the temperature has increased beyond the set point, we have to open the valve, the controlled action will take place, and accordingly the valve will be opened and more water will be flowing through the cooler chamber itself, and the cooling will be more. In the other way around, if the temperature is less, then you can allow a oil to be a water level or water flow rate to be less. So you can close the valve. So this way, this is controlled. So this is a very fundamental feedback control system where the controlled variable is the lube oil temperature that you want to maintain, and the manipulated variable is the water flow rate. Okay. Now, if I want to draw the block diagram, so how the block diagram will look like? Because this is a schematic, or this is the actual scenario. I don't think if I can put both the pictures in the same slide. That's the point. I think this logical schematic diagram is very easy to follow. Or what I can do, let me do one thing. Just a second. Is it visible? দেখতে পাচ্ছ? Okay. I think this arrangement is much better, right? So you can get one-to-one correspondence with each of the things, right? Now, this, let me just connect this thing. This is a set point. This is a reference of the set point. I'm just drawing the process control block diagram. Okay, the equivalent block diagram. This is the set point. Now, the set point requires the feedback signal. How this feedback signal is available? This feedback signal is available from this temperature transmitter. So this is your temperature transmitter. It measures the temperature of the exit lube oil. This is the controlled variable, the controlled output, lube oil temperature, and it converts that particular temperature to an equivalent signal. This is called a feedback signal, which is at par or at the same level as the reference signal, so that this can be compared. That can be plus or minus, positive or negative. I think I have discussed this positive and negative feedback. And normally we use negative feedback signals to generate the error signal. Right? This error signal is nothing but something like this: set point, actual value is coming. So this will be the error signal at here. This error signal will then move to the temperature controller, like this. In this scenario, you can say the temperature controller can include this summation block or the error detector. Same. So based on this, actuating signal will be generated. This signal is drawn like this. This normally means a pneumatic signal. So pneumatic signal will be given to this temperature control valve. So this actuating signal will actuate the temperature control valve, or it will make the temperature control valve open or close. And correspondingly, depending upon if you are opening or closing, correspondingly, this cooling water flow rate will be adjusted. So that becomes the manipulated variable. This is a manipulated variable, the variable that is manipulated. So that this lube oil temperature as a controlled output, the controlled variable, you can say CV, attains the desired value of this set point value. So this is the basic control loop. Okay, that constitutes the fundamental block diagrams. This is a block diagram from, and this is obviously the actual schematic, the layout, and this is the block diagram corresponding to that schematic. I just remove this. So this is how you can put a particular schematic into a block diagram, and you can also recollect, or you can also connect this definition, the why the error signals actually actuating is actually appearing, why this is called a manipulated variable, why is a feedback signal, okay, what is the controlled variable. So these signals, this can be easily interpreted in terms of this block diagram as compared to this schematic diagram. So this is the first task of a process control engineer, to develop this block diagram sort of things. Okay. Now there's a catch. So it may seem from this diagram that this temperature control system is very easy. What you have to do, you have to merely measure the temperature of the lubricating oil using a temperature transmitter. Then the temperature transmitter will give you the signal that you have to compare with the set point, and accordingly you have to open a close a valve. Right? It seems very easy, very elemental or trivial. Okay, it's trivial. It's very, the ideology is very simple. But whenever you are looking on the practical perspective, it is very, very difficult because of a very particular property of this process control, which makes this a very, very difficult thing. And this particular property is called, it can be categorized under this head, that is process time lags. I think if I'm not mistaken, I've already mentioned something that in a process, the time delay is there. Okay, there will be physical time delay or time delay due to other phenomena. That time delay means as soon as you make some correction, the result of that correction will not appear instantaneously. It will require a certain amount of time before The results can be reflected in the output. So that is called the process time lag. Now this process time lag can be a result of three very fundamental properties of a process. What are these fundamental properties? One is capacitance. Any guess what will be the third one? Anybody else? Certainly not. Certainly not. You'll get to know. You'll get to know. Transportation time. Okay, you'll get to know. You'll get the idea when I define these things. First of all, what is the capacitance? Before you define these properties, you should always keep in mind that there is an inherent characteristics of any process or system that tends to delay or retard any changes in the values of process variables that you intend. There's an inherent property of retarding or delaying the change. So this very particular property can be classified under these three heads. Right? Now, suppose it's a very common thing. If I tell you, since you're quite matured now, if I tell you some notion to follow, you cannot follow that instantaneously because you have that resistance. No, no. You have to first convince me. Then I'll make that modification, or then I follow that notion, right? And what is the capacities? Because you have so far acquired a particular viewpoint towards life or towards this particular motion. If I ask you to change that, it will not be very easy to change that instantaneously because we have a mentality that is grown towards a particular path. So what you have to do? I have to overcome that. For that, the change will be ultimately there if I can convince you, but that change will not be instantaneous. There will be some time lag before you get convinced. And the transportation time is something completely different from this resistance and capacitance. So the property of delaying or retarding any change in the value of process are these three properties. First of all, what is the capacitance? The capacitance is nothing but the ability of a process to store energy. That's important. It is quite analogous to electrical capacitance, right? The capacity of a system to store some energy. Now, what are the capacitive elements or where you can find this capacitance? This capacitance in this particular example will be found on the walls of the tubes of the Liouville cooler, right? The tubes that are flowing in the Liouville cooler, that wall has some capacity to store some energy. The cooling water, it has a capacity to store energy. Okay, and the Liouville chamber itself, there's the Liouville itself has a capacity to store the heat energy. Therefore, this energy storing property, what it will do, it will have that tendency to retard any change. How? Suppose you see that the temperature of the output lube oil is more than the set point. So instantaneously, what you will do, you will open the control valve so that more cold water will flow to the lube oil cooler. Now, if you expect that instantaneously, as soon as you open the valve and the water flow rate increases, instantaneously the lube oil temperature will change, it's not true. Because you cannot take away the heat stored in the lube oil tube wall or the lube oil itself instantaneously. Because it has some capacity and you have to give some time, or some time has to elapse before you can take this amount of heat with this excess amount of water, cold water, right? So it will take a particular amount of time before the temperature drop in the outlet oil flow will be seen. So there will be a slight delay because of this capacitance property, the lube oil or the wall of the lube tube wall, the tube through which the lube oil is flowing, that wall will tend to retard the change in the temperature because there is a temperature gradient. Heat will be transferred, but it will not be instantaneous. So this is a property due to the ability to store energy. Then naturally the next question comes, then what about resistance? The resistance is that part of the process that simply opposes the transfer of energy between the capacities. What does that mean? See, lube oil is a capacity, it has the capacity to store energy. Cold water, since its temperature is low, it has the capacity to store energy and it will tend to draw heat from the lube oil, which is at a higher temperature, right? So this change of energy between two capacities will be resisted by the walls of the tube through which the lube oil is flowing. So the tube wall will be providing a resistance to the flow of this energy. So this resistance will obviously be a retarding force or delaying force. Due to the presence of this resistance, again, it will add to that capacitance. Due to the presence of this resistance, the temperature change. We have excess water, cold water flowing in. But that cold water cannot instantaneously take away the excess heat to reduce the temperature. It will take some time due to the capacitance and due to this resistance that is facing, right? So this is another point, the resistance. It is also analogous to electrical resistance, right? The third point, which is a bit different, is the transportation lag. So this thing is nothing but plain and simple time delay. That is, it has no other physical property. It's simply a delay, a physical time delay in process. Why? Why I'm calling this a time delay? Because if you have made some change in one portion of the process, you cannot expect that change to have instantaneous effect at a place which is located far away. It will have, it will require some time before the change can be reflected at that far away point, right? How? Say for a very simple example, I have we have incorporated a temperature transmitter at the cooling at the oil output, which is supposed to be cold one. If you can place this temperature transmitter just outside this chamber or 1 meter away from the chamber, 2 meters away from the chamber, 5 meters away from the chamber. If you put it 1 meter away from the chamber, the cold oil after leaving the chamber will be soon detected by the temperature transmitter. But if you put it 10 meters away, it will take some time before it can be detected, right? Obviously, there's a continuous flow, but the change has happened, but that can only be detected after it has traversed through this 10-meter path. So there will be particularly a dead time or delay time, say delta t, after which you can only detect. The control action has done its job. But still, after this delta t time, your set point will be reached via this temperature transmitter because it is located far away. If you can locate it close enough, then this delay will be reduced. But it cannot essentially make it zero. Okay, there will be some distance. So it will be the physical distance or the physical time delay in a process that you encounter in a physical system because you cannot put these sensors at in any position. There are some arbitrary positions which are already determined for the sensors to be put because they require a particular environment where they will give you a full potential of their operation. So that you have to put the sensors at adequate and predetermined place, not arbitrarily at any place, right? So this is how this time lag or the transportation time will contribute to this process time lags, right? And again, I'm reiterating, this is not a process of retarding or delaying the change. This is a physical time that elapsed between two consecutive operations, and you cannot, sometimes you cannot avoid that, right? So these are the three components that makes the control problem very difficult in actual scenario as compared to as the same from academic point of view, right? So let us move on. I'll send you a PDF that will constitute some different examples of different types of processes. I'll not indulge into that. What I intend to do is to give an introduction to a basic control scheme and how a particular process control can be modeled, right? Because if we go by the definition that what is the purpose of the primary objective of process control is to maintain any process at desired operating condition safely and efficiently while satisfying environmental and product quality requirements. So this is a primary objective. Now this desired operating condition is determined by the process engineer or the designer itself. Right. Now a process control constitutes of two fundamental components of study. What are these two components? Number one, process dynamics. This is nothing but modeling of the process, where you study the dynamics of a process, you model the process through integral differential equations or any other equation, any other form that you find suitable. There, we shall discuss about this. Modeling part, this is the one part, modeling, and the second part is obviously process control part, okay, which will be much more important. But without this process modeling, you cannot proceed to process control part. Now, I'll just make one point here that in study of a process dynamics, there are two parts. Sorry, I think I should use a separate, since it's under this process modeling. We can study the process behavior at steady state, or what we call equilibrium condition, or you can study the process behavior during the transient condition. These are the two dynamic studies that you can go through. Now, the steady state or equilibrium condition study means it involves only the material and energy balance. That is, the system, the process control is, or the process system is running at a given or in a desired position, desired state or condition, where an equilibrium is reached. Now, if under any condition, due to a disturbance or in change in operating condition, or by deliberate change in desired position or the desired condition, there will be a situation where this equilibrium will be shifted. Suppose initially it was working with this value, now it is shifted to this value. But this transition from this value to this value will not be a smooth one. It may follow different paths. It can follow a path like this. It can follow a path like this. Right? So there are different paths of achieving from this equilibrium state to this equilibrium state. And this study is obviously the transient study. So we'll consider both the modeling of the process study of process dynamics during steady state or equilibrium state, and also the study of the process during the transient. Now, when these transients may occur, I have already mentioned that the transients may occur during startup and shutdown, right? During the startup process and shutdown process, this transients may occur. And if it's uncontrolled or unaccounted for, you may have some adverse situations like this. So this overshoot of this process variable may be very detrimental. So you have to make sure that this transient due to shutdown, during the shutdown or startup process, or due to unusual process disturbances, or due to the planned transition from one state to another state. That is, suppose this product is running at 1,000 bottles, 1,000 units per hour. We want to increase it to 1,500 units per hour. So there will be an uplift, there's a shift in equilibrium for all the states or all the conditions. These changes should not bring about such uncontrolled or unconditionally high level of process variables. They should all be bounded. So this study is very important, this transient study. And ultimately, the final goal is to reach the desired equilibrium. The equilibrium study is important, more important in this sense. But you cannot avoid this transient study as well, because that may cause some detrimental effect on the system, not only in performance, in physical, physical damage may happen. Now let us consider a physical example. Okay. We shall consider a stirred tank blending system. Now our objective is to give you an idea about what is meant by control and why it is necessary, and then what are the way you can achieve a particular control. A very brief overview, because I have only 15 minutes left, so I will give you a very brief overview. So I'll have some notes prepared here. So let us start with the first phase. As I already mentioned, the first phase in a process control is a design. Okay, so if we see the scenario, sorry, I think I should first describe the plant or the plant we are dealing with. So this is a blending system where this stream one, sorry, this color is not visible. This stream one is a mixture of, say, two components A and B. It is a flow rate W1, right? You can consider for the time being W1 to be constant. And what is X1? X1 is the mass fraction of A. That is the composition or the concentration of A in the mixture of A and B. This X1 is suppose variable. W1 is fixed. It is put into a stirred tank. There is a constant stirrer there. The other stream, the stream 2, is of pure A. So what will be the concentration or mass fraction of A? X2, that will be equal to 1. It is constant. The flow rate is W2, which can be controlled by use of this control valve. So W2 is a manipulated variable, the only variable that you can manipulate. So W2 is a manipulated variable. Now what is our objective? Our objective is that the outlets mixture, which is obtained by this overflow line, as soon as this tank overflows, you get this outlet stream, should contain a mass fraction of X that is equal to XSP. That is the set point value. That's the output concentration, or the concentration of A in the output stream or outflow stream is given. And obviously its stream flow rate is W. It's also given. So you have to maintain a stream flow rate of W at output with mass fraction XSP for component A at the outlet. So this is a control problem. Here X1 is variable, W1 is constant. So X1 is the only variable, and it is kind of a disturbance. So you do not have any control over it. The control that you have is on W2 only. That is it's a manipulated variable. What will happen if X1 changes? Then concentration of X will change. Correspondingly, you have to increase or decrease this flow rate W2 because it is purely of A, so that you achieve this desired value of concentration of X in the outlet stream. Right? Let us see how we can design this. First of all, you have to design this system, right? So that this XSP is exited at the output, we get that particular concentration at the outlet. So the design question is, if the nominal value of X1 is X1 bar, There is the normal flow rate, and the nominal flow rate of W2 bar is required. The bar means these are the nominal values at equilibrium point or steady state. So to nominal flow of inflow rate, if it is x1 bar, then the outflow, the inflow rate of the stream 2, W2 bar, that will be required to produce the desired output concentration of XSP. What should be this W2? This is the question. If x1 is given, a nominal value is given, then what should be the nominal value of W2? For that, you have to consider the overall balance, flow balance, W1 bar plus W2 bar, both the inflow rates, minus W bar, the outflow rate, should be equal to 0, and the component A balance. In the first stream, x1 is the concentration and W1 is the flow rate. In the second stream, x2 is the concentration, W2 is the flow rate. And in the outlet stream, x is the concentration, x bar, and W bar is the flow rate. All these are steady state material balances, right? This is very important. That's why these bars are put. Now all know x2 bar is equal to 1 as given. There's no way you can change that. And x bar is nothing but your desired XSP. So if you can rearrange these equations now, let us see what happens. By rearranging this equation 1 and 2, we find out the desired value of W2 at steady state, the stream 2 flow rate, to maintain x bar equal to XSP will be given by this equation. Now, this is known, this is known, this nominal value is also known, this is known, so we can easily calculate this. So the W2 bar will be the function of this x1 bar, since we have considered this to be constant. Now, what will happen? This x1 may vary with respect to x1 bar, and corresponding to that, the W2 is to be varied accordingly, right? So this is the design problem. The control problem is that, I'll just put the control problem over here. So this is the equivalent, the equilibrium equation, or the equilibrium value of W2 that is required to produce an outlet stream with concentration XSP. Now the control question is, suppose the inlet concentration x1 varies with time. Then how can we ensure that the outlet composition X will remain at or near its desired value? This is the problem. X1, the inlet concentration in stream 1 of component A has changed. Now you have to ensure, even under the changed condition, the X remains near or the desired value of XSP. The change can only be made via the flow rate W2 through this control valve. Let us see how these changes can be. প্রবলেমটা বুঝতে পারছো তোমরা? এই x1 টা চেঞ্জ করছে, W2 টা কিভাবে চেঞ্জ করলে এই x টা তোমার মেইনটেইন থাকবে। Okay. First method, what you can do, you measure the controlled variable. You put in composition analyzer in outlet stream. It measures the value of X in outlet stream, and this value is then compared in a composition controller where there is already a set point given, and if it is more than set point or less than set point, accordingly this valve will be opened. See, if x1 is greater than x1 bar, for which for x1 bar it is, we know, W2 bar. X1 is greater than x1 bar, so the concentration of x1 in the inlet stream has increased. So what should be the operation on W2? What should be the value of W2? It should be greater than or less than W2 bar. Bolo? W2 bar yields X equal to, because our objective is to make X equal to XSP. Right? W2 bar makes this X equal to XSP for X1 bar. Since X1 is now greater than this, then what will be? condition between W2 and W2 bar? Anybody?
So greater than W2 bar.
Greater than হবে?
স্যার লেস দেন বোধ হয়।
ঠিক করে হবে, greater than না less than? কেন
স্যার
less than হবে?
কনসেন্ট্রেশনটা কমাতে হবে এক্স এর, x1 এর।
Right. The other case will happen when এটা যদি sorry যদি কনসেন্ট্রেশনটা কমে যায়, তার এখানে তো কমে যাবে না, তখন তোমাকে এখানে বাড়াতে হবে। তাহলে এখানে বাড়লে এখানে কমছে, এখানে কমলে এখানে বাড়ছে। there is something kind of a mirror or inverting kind of a expression. So if we write down in terms of a simple law, can you write down this W2 is like this? Then what is the value of Kc? Kc greater than 0 or Kc less than 0? If I write down this, বলো Kc কি হবে? Greater than 0 না Kc less than 0? এটা বলো।
স্যার লেস দেন 0।
Sure? ভাবো W2 T minus W2 bar is equal to Kc XSP minus XSXT. ধরো x1 বেড়ে গেল, তাহলে x কি হবে? বেড়ে যাবে তো। এটা কি হবে? যখন x1 যদি গ্রেটার দেন x1 বার হয়, x টা বেড়ে গেছে, তাহলে লেস দেন 0। তখন আমাদের বাল্বের কি অপারেশন দেখলাম? W2 তখন কি হতে হবে? should be less than W2 bar। তাহলে এইটা হচ্ছে less than 0 হতে হবে, লেফট হ্যান্ড সাইডটা। এই পোর্শনটা less than 0 হয়ে গেছে। অনলি সিচুয়েশন এটা সম্ভব যখন Kc greater than 0 হবে। বুঝতে পারলে? তোমার x1 টা বেড়ে গেছে x1 বারের থেকে,
আচ্ছা
তাহলে এটা নেগেটিভ। তখন আমি W2 is less than W2 বার, এটা তো নেগেটিভ হতে হবে। অবভিয়াসলি এটা নেগেটিভ, তাহলে এটা অলরেডি নেগেটিভ আছে, তাহলে টোটালটা নেগেটিভ থাকতে এটা পজিটিভ হতে হবে। তাহলে Kc should be positive, right? This is a very easy proportional control law where the control action will be determined by the error multiplied by proportional gain Kc. I will discuss it later when the situation comes. So this is the first scheme where we are measuring the controlled variable itself and generating the control action based on the deviation of the controlled variable with respect to set point, right? So what is this control law? You can term this as কি বলবে এটাকে, এই মেথডটাকে? This will be termed as feedback control, right? কন্ট্রোল ভেরিয়েবলটাকে তুমি ইনফরমেশন নিয়ে ফিডব্যাক করছো, নিয়ে তোটা দেখাচ্ছো। আচ্ছা, এক্ষেত্রে সাড়ে বাঁচতে গেলে আমরা 5 মিনিট লাগবে। If you wish, and those who have class from 6:30, I don't think everybody will be having class. তোমরা সবাই কি ক্লাস আছে? হ্যাঁ, যদি কারো থাকে ইউ মে জাস্ট আস্ক এন্ড লিভ, ওকে? তুমি বলে লিভ করতে পারো, কোনো অসুবিধা নেই, ক্লাস শুরু হয়ে যায়। আমরা 5 মিনিট লাগবে, আমি থামতে চাইছি, এটা করে দিই আজকে, ভিডিওতে পেয়ে যাবে তোমরা, ঠিক আছে? So this is the first method where you are measuring the actual controlled output, and based on that you are generating the control action and manipulating the manipulated variable W2. Now next scenario, what we'll do, we'll measure x1. We'll be measuring x1 itself, and based on this measurement we'll control W2. That is, we're measuring what is called a disturbance, because x1 is a disturbance, is uncontrollable. Whatever the scheme, we're putting the same the composition analyzer in the inlet one stream to analyze the composition of X1. And this is fed to the composition controller. It has in its reference X1 bar as a set value. It knows if X1 bar is there, I have to have a flow rate of W2 bar. This is the nominal value that is set. Now, any change in this X1 will cause an error to appear here. This error, the actuating signal, this will correspond to an actuating signal, will cause this control valve to open or close, so that the output concentration of A in the outlet stream is maintained at the desired value x equal to x square. বুঝতে পারলেন? আগেরবার করছিলাম কি, we are waiting for the output to get deviated and then we are taking the control action. In this case, we're not measuring the output itself, we're just measuring the input and measuring the particular element or particular property, variable that we term as disturbance. So even before the disturbance reaches the system, when measuring that, we are detecting that okay, there's a change in the composition in stream 1, and accordingly we are taking a control action. But in the previous case, the control action is only taken once the controlled variable or the output has deviated from the desired value. That's why a feedback was sent. Okay, this data is deviated. So you can now take corrective action. In this case, even before it is deviated, the corrective action is generated. That's why it is termed as, any guess? Okay, sure, Shugato. So any guess what it will be called? If it is feedback, then it is?
Feed forward.
Right, feed forward. Very common thing. There is a subtle difference between this feedback control and feed forward control. I'll come to it very soon. Now, I'll just put, now how this feed forward control law can be written or can be decided. This can be decided based on this logic. If x1 is greater than x1 bar, so what do we have to do? If x1 is greater than x1 bar, then what do we have to do? We have to decrease W2. So W2 is less than W2 bar. And if x1 is less than x1 bar, they increase W2. This is a very simple logic that we already developed. But based on that, this will be the control law. This is nothing but a slight modification of the equation that we have decided in the design phase, where this W2t will be a function of x1t, and this is the nominal value of W1 bar, and XSP are the set point values. That is the nominal value that you desire at the output. So this is how we can calculate this W2t or the flow rate based on this x1t, provided we assume that a W1 is fixed and XSP, the set point, is obviously fixed. So this is how a feed forward control law can be implemented. These are two control aspects. The third one is that you can measure both x1 and x and take corrective action accordingly. Now, why we need to measure both x1 and x? This is very important to know. See, in the first case, the main disadvantage of this case is that as soon as this x1 varies, x will vary, then only this W2 will be changed and it will come back to its previous value. So there will be a certain deviation of x from the desired value. You cannot avoid that. But in this case, there is a provision that you can detect this change even before it reaches the system. So if you can make certain arrangements so that as soon as you detect this, say 10 meters before it reaches here, so the time it takes to reach here, by that time, if the controller can open the valve and the flow rate reaches a new steady state, W2, which is calculated based on that law. So what will happen when it reaches here? It has already adjusted. So the concentration of X will not be affected at all. Do you follow that? মানে সিস্টেমে এফেক্ট করার আগে তুমি ডিটেক্ট করছো এবং কারেক্টিভ অ্যাকশনটা নিয়ে নিচ্ছ, তাহলে কোনোভাবে সিস্টেমটাকে এফেক্ট করছে না, রাইট? So this is the beauty of this feed forward control. Now I will put an open question. So in this scheme, whichever one will you prefer? Method 1 feedback or method 2 feed forward? বলো। Anybody? বলো।
জানি না স্যার।
কেন জানো না কেন? কি মনে হলো কথাটা শুনে, কি মনে হলো? দেখো একটা যেটা বললাম, আউটপুটে ভ্যারিয়েশন হবে, তারপরে ওটা কারেক্টিভ হয়ে কারেকশন হয়ে আবার সেট ভ্যালুতে ফিরে আসবে ফিডব্যাকে, মেথড 1। আর মেথড 2 তে আউটপুটে কোনো ভ্যারিয়েশনই হবে না, কারণ তুমি আগেই কন্ট্রোল অ্যাকশন নিয়ে নিচ্ছ। তাহলে কোনটা প্রেফার করবে? লজিক কি মানে বেসিক কি বলছে, কমন সেন্স কি বলছে?
মেথড 2 লাগছে স্যার।
মেথড 2 এক্স্যাক্টলি, তাই তো? সবাই এগ্রি করছো?
স্যার ফিডব্যাক তো সবসময় স্টেবিলিটি বাড়ায় কোনো সিস্টেম।
একদম বাড়ায়, ঠিক, গুড পয়েন্ট। ফিড ফরওয়ার্ড কি স্টেবিলিটি কমিয়ে দেয়? এমন কোনো প্রমাণ পেয়েছো?
না স্যার সেটা
না, এখানে এটা ঠিকই আছে, তোমাদের পয়েন্টটা একদম ঠিক, কিন্তু একটা পয়েন্ট এখানে মাথায় রাখতে হবে। আমি যে বললাম, এটা সবসময় খেয়াল করবে আমার কথায়, যে it is detected before it reaches the system, but if it is possible to take the corrective action, if টা খুব ইম্পর্টেন্ট। কারণ দেখো, আমার এখানে একটা definite closed form-এ have a mathematical expression that relates x1, x2, w1, w2, because this is a very simplistic system. And we're assuming that the stirrer that is there is an ideal one and its efficiency is very, very high. As soon as that water comes in, it can blend it. But that is not a phenomenon. সবসময় কিন্তু এত বড় স্টাইরিং হয় না। Plus, all the systems are not that simple or easy to formulate. সেখানে তুমি যে কন্ট্রোল অ্যাকশনটা নিচ্ছ, যে ইকুয়েশনটা আমি দেখলাম, এই ইকুয়েশনটা স্ট্রেট ফরওয়ার্ড নাও হতে পারে। It's some cases it's very difficult to obtain a straightforward equation like that. For that case, it will be very difficult to achieve this sort of a feed forward control. Major problem, one major problem, even more major than this, what I've mentioned, is that this feed forward control requires the information that which of the variables that may vary in a process system. In this case, there are two variables. You have assumed that x1 is the variable one. So we have taken this corrective action for the academic purpose, for the time being. Let us assume it's ideal and it doesn't allow any deviation in x. Very good. But what will happen if this w1 changes? Because there is no provision for measuring this w1. If x1 remains constant, w1 changes, x is not measured. See, here x is not measured at all. So w1 changes. You are saying, okay, x1 তো ঠিকই আছে, তাতে কোনো কারেকশনের দরকারই নেই, তাই না? তো w1 যদি চেঞ্জ হয়ে যায়, সে তুমি ডিটেক্টই করছো না, not detecting w1. So what will happen? The output concentration of A will be completely different from the desired value because no corrective action is taken. So the limitation of feed-forward control is that feed-forward control is only applicable for measurable disturbances, the disturbances that you can measure. Now you may ask, so W1 is also measurable. Exactly. To make the system even more robust in the sense, what you have to do, you have to put another loop where you have to measure W1, put another controller, put another control action to the valve that will act on the change in W1. Then you can say, for this purpose, then now, okay, now this is a complete feed forward control scheme that we achieved, right? You may be satisfied at this point, but I'm not. Why? Suppose W1 and X1 are at perfect value, but due to some other anomaly, due to some styler has stopped working, it's not actuating at the perfect range or the rotation speed that you require from it. So what will happen? Momentarily, this X may vary, and there is no provision of having a check on this X because this is the control variable. The variable they want to maintain a desired value. So if you do not make any provision for measuring that, how can you expect that it will remain in the same value? Now come back to the feedback control. In the feedback control, I have not measured X1, I have not measured W1, I have not measured any loss of operation, lack of operation in the styler. What I've done, I've only measured X, single variable. But I can assure you that this will ensure the robust performance or the performance of the system to follow more or less accurately the desired value of X under the influence of variation in X, variation in W1, or any lack of operation of the styler because it doesn't require any other information. The feedback control requires only information whether the controlled output is at set point or not. If it is not at set point, find the error, take corrective action. It doesn't bother why this set point is deviating from the set point. It doesn't bother. It is a manipulated variable, it is a control law that is well defined. Whenever the set point changes, it takes corrective action and makes it correct again. So this is the power of the feedback control. Without any measurement, without any knowledge. Now, as we go on, we'll see that plant model plays a very important role in the control system. And if you can recall, in feedback control system, it never requires a very accurate plant model. An abstraction of the plant model will be enough because any discrepancy in the physical plant and the model can be taken care of by these feedback characteristics of this feedback system. Because at the end of the day, it will make the control variable to follow the desired value. Whatever model you start with, it has this capability of correcting for any error in the loop. So that is the beauty of a feedback control system. Whereas in feed-forward control system, you require definite information regarding W1 and X1. And you have to need to find out all the possible disturbances. So obviously the complication is much more. And most importantly, you need an exact mathematical formulation to generate a control law like this. Until or unless you generate a definitive control law like equation 5, you cannot apply this feed-forward control. And this mathematical model based on which you are developing this control law should be accurate to the level. Otherwise, there will be discrepancies and you will never achieve that particular level. Now, next question that you may ask, then why should you go for feed-forward? See, in situations where you have a definite idea about the possible disturbances that are more likely to happen in a system or occur in a system, you can apply a feed-forward control for that because that has the capability of correcting the system variables or manipulated variable even before it affects that control variable. That's a good property. It's a very beneficial property. But you cannot simply rely on that. What you have to do, you have to augment this with, you never write this like this, sorry. Shouldn't write in this like this. You have to augment this feed-forward with a feedback control. So even if the feed-forward control fails due to some other unaccounted for disturbances, then feedback will take care of that lack of operation. And it will ensure that the system will operate at the desired level or the desired operating condition. That's why the third proposal will be a combination of feedback and feed-forward control, right? So that it not only eliminates the effect of measured disturbances, it also accounts for any lack of operation due to unmeasured disturbances by this feedback control. So most control systems, whenever we apply a feed-forward control, we never rely completely on that. Feedback control is also provided as a supervisory one, as a contemplating one. Then you have to compensate the entire system not only using feed-forward, feedback. So feed-forward, feedback composition or the combination is the way to go to solve this problem. And last but not the least thing, that is obviously not a control part, but you can say that any change in x1 will be reflected in x, right? Now, if you can make this capacity of this tank very large, say if you can increase the capacity by 10 times, then the effect of this x1 on x will be very, very less. That can be proved. Because in a large capacity tank, due to the capacitance property, okay, it will retard the change in such a way that this change will be very less, and the deviation, there will be certain deviation in the feedback control system before it comes back to the desired value will be much, much less. If you can draw it, suppose in normal situation in this tank, it is following like this, but if you apply the increase the volume by 10 times, it may follow like this, but the deviation will be never this exceeding value of this much. In this case, it will almost follow it. A very slight deviation will come because of the large capacity of water intake in the tank. Right? So this is another way, but that is not a control scheme. So if we summarize the control schemes, these are the 4 control schemes. Method 1, you measure the control variable and change the manipulated variable, that is a feedback control. You measure the disturbance variable and change the manipulated variable, feed forward control. Last one, you measure the disturbance variable, dB, and the controlled variable, and manipulate the manipulated variable, that is a combination of feed forward and feedback. And last one, design change, where you need to change the tank to increase the capacity. So this is an entirely new scenario. There is no control required. So these are the different aspects of the control that we can think of to tackle this simple problem. So we're introduced to the concept of feedback and feed-forward control, the relative merits and demerits, and why we normally use feed-forward control in combination with feedback control to ensure the proper operation of the entire system. Right? I'll conclude this lecture since I have introduced this diagram to you with this process control diagram. Now, the purpose of this, I'll just explain very briefly because I want to make it very clear at this point that the level, the different signals that you see. Now, first, the set point is a mass fraction. Okay, it may be moles per kg. But a digital controller or a controller may not be able to handle this. So what we have to use, we have to use an analyzer calibration. What does this do? They convert this value to its equivalent, and which is in terms of milliampere in an electrical signal. It may be milliampere or it may be millivolt. Since I'm considering the current actuated system, it will be in milliampere or say in millivolt, whatever. So now this analyzer calibration is done within the controller itself. You just feed the required value of mass fraction in moles per kg, whatever. So what it will do, it will calibrate that and convert it to equivalent milliampere range. Why this is required? See, at the output side, we are measuring the mass fraction in say same unit, moles per kg, the actual value of the control variable. Now this analyzer is here again, where the sensor that senses this moles per kg, the sensor data has gone through this analyzer calibration unit, and it has been converted to this XMT, the measured value, and it has same scale or level milliampere or millivolt. There will be a calibration, obviously, where this moles per kg will be calibrated or converted to milliampere and millivolt range. Once you put it to either milliampere range or millivolt range, then you can compare them because they are not equivalent level. So this comparator will do the comparison and generate the error signal, which will again be in milliampere or in millivolt. Depending on this error signal, this feedback controller will develop the corrective action, right? PT, which will be again in milliampere and millivolt. This will move on to the final control element or the actuator. There's a control valve where it will be current or voltage operated, and accordingly, the valve will open or close. The opening or closing of the valve will control the manipulated variable. There's the flow rate. Sorry, I should not write MV because it will be confusing. I'll be writing like capital M, capital V, manipulated variable, which again is a unit kg per second. Now, because it is now again come back to the physical unit, because the flow rate is a physical unit. The control part ends there. Entire control part is the controller in the block. This is the control or instrumentation part. And outside this instrumentation part, this green region is the actual physical system. But this is a manipulated variable calculated based on this feedback controller. Feedback control action that causes the valve action, which is the final control element. And obviously, this will cause the output of the stir tank to reach this desired value. And here, what are the disturbances? The disturbances are the change in the mass fraction, a change in the flow rate of stream 1. That is, change in the mass fraction in stream 1 or change in the flow rate in stream 1. Any disturbance can be taken care of by this feedback control scheme. Now, my main purpose of using this figure is to make make this idea clear. That what are the levels of signals that you normally encounter in a process control loop? This is a physical signal, physical signal, physical signal, physical signal, physical signal, physical signal. And these are corresponding equivalent control level signals, the radons. And that has been calculated based on this calibrated analyzer calibration, right? So this is how an actual process control operates. বোঝা গেল যে জিনিসটা ওখানে দেখে যেরকম মনে হচ্ছিল অত সোজা না, এখানে আরো কিছু তোমার সূক্ষ্ম সূক্ষ্ম ব্যাপার আছে, very fine things are there. This idea is very very important, right? যে কোন অবধি আমার কন্ট্রোল পার্ট আছে আর কোনখানে তোমার পাওয়ার পার্টটা আছে, and there should always remain an isolation between them, right? কোনোভাবে যেন পাওয়ার পার্টটা এসে কন্ট্রোল পার্টটাকে ডিস্টার্ব না করে। ওই জন্য অ্যানালাইজার ক্যালিব্রেশন করে আমরা লো পাওয়ার লেভেলে নিয়ে এলাম। কন্ট্রোল কম্পিউটেশন তুমি করতে পারো ডিজিটাল কম্পিউটার দিয়ে হচ্ছে কিংবা মাইক্রোপ্রসেসর দিয়ে হচ্ছে, সেখান থেকে আউটপুটটা দিচ্ছে। অবভিয়াসলি এর মাঝখানে অনেক কিছু বাদ দিয়ে গেলাম, যে তোমার লেভেল স্টেপ ডাউন স্টেপ আপ হ্যাঁ করতে হয়, পাওয়ারের একটা সেপারেশন আইসোলেশন রাখতে হয়, এটা তোমার ইনস্ট্রুমেন্টেশন পার্টে পড়বে। আমার তাও মনে হলো কন্ট্রোল পার্টে যখন পড়াচ্ছি তোমাদের এই ডিস্টিংশনটা থাকা দরকার, যে হোয়াট ইজ এ পার্ট অফ দ্য কন্ট্রোল এন্ড হোয়াট ইজ নট, what are the components of the control part, what are the signals associated with the control part, and what are the signals associated with the physical system or the process itself, right? So I guess I'll stop here, right? Any questions?